So today we're going to be discussing modeling disorder with AFLOW. It's a tricky topic, so we're going to go through the command line very slowly because there's going to be a few inputs that we have to be aware of, and it's a very large extension of some of the proto commands and the AFLOW proto commands that David presented yesterday. So so what is disorder? So we've been going with this premise that we have a macroscopic structure that can be reduced to a set of atoms in the form of a crystal. So we can reduce space because there's a great deal of repetition in the information, and so we have order, we have symmetry, of periodicity, and so all of that goes into having a nice crystal structure with a very few number of atoms. But that's very ideal, and in the real world everything has disorder. Okay, so there are very few things, I guess, in physics that display sort of a perfection or an absolute. I mean, you might imagine something like superconductivity, but and you know, there's even the disorder is apparent in every sort of structure material that we're dealing with. It's just whether we choose to model it or not is really the question. So modeling disorder is intrinsically very, very difficult. It's very expensive. And so we're going to talk about some ways that we can do this in a high throughput way. So there's a lot of different types of disorder. Two of the main ones that I'll be discussing today, they include structural disorder. So something like glass. Glass is a disordered structure. It doesn't have the translational periodicity that you would see in a crystal. So you see that this crystal structure has its repeating units, and in glass you don't see that structure. Okay, so you don't see that repeating structure. There's another type of disorder associated with the chemistry of the material. So the concept of having an atom occupy a single site is something we've been taking for granted. Okay, so you know, we have these sites in the crystal here, and we've assumed that each site has been occupied by one atom. Okay, and so a way of thinking about disorder in a chemical with respect to the chemistry is that maybe we'll have what's called partial occupation. So instead of just having the site singularly occupied by sulfur or selenium, we'll have a site that's going to be partially occupied or randomly occupied, depending on which snapshot you look at. By 25% of the time we'll see sulfur, and 75% of the time we'll see selenium. But I'll go over that in detail more in the later slides. We're going to focus on that first, so the chemical one. Okay, so why is disorder important? I mentioned that disorder appears in nature, but a great deal of modeling disregards disorder. So is it even worth studying? So yesterday we talked about the convex hull and understanding whether materials are going to form, and so we have this structure of understanding the difference in the energy with respect. So we have a mixture here of palladium, platinum, and then we have the pure components of pure palladium and pure platinum. And I said that just graphically, if the mixture is more stable than the components, then it's going to be lower in energy than the tie line here. Okay. So we called this the enthalpy of formation because we've zeroed out the endpoints which have energy, but we've subtracted them off to zero them out. So this quantity here of the enthalpy of formation in the fact that we're looking at a mixture of two components, you can also think of it as an energy gain from going from one species, one component, to going to two. Okay, so we actually gain energy. There's an energy gain here. Okay, so that's a new terminology that I want you to think about. There's an enthalpy gain that we have in terms of going from a single species to one that's two species. Okay, and now we're going to generalize that concept to 3 dimensions. If we have a ternary convex hull, we have 3 components. We can ask the question, what is the enthalpy gained from going from a system that only has 2 components to one that now has 3? Okay, so yesterday I showed you what the convex hull would look like if we only form it using just binaries and unaries, so 2 component and 1 components, and then we added a single ternary system. Okay, so now this system here is lower in energy, and you can see that in this example, it's going to have a very large impact now in the convex hull. It's gonna recreate these facets, and so now we're going to have this point existing on the convex hull. But now this point, this is the enthalpy gain for this single point. Okay, and so we can generalize that for n species. What is the enthalpy gain from increasing the number of components here? Okay, so I showed you what that looks like in 2 dimensions and in 3. In 1 dimension, this is the concept of the cohesive energy. So for those of you that have studied, I learned it in solid state, is the concept of what is the energy of a single atom in space versus the crystalline form. Okay, and so that's what we call the 1 here. This is the cohesive energy, and so it's a very large number. And you can see there's a pretty clear trend. So if we look at the enthalpy gain as we increase the number of species, we did this analysis for all of the data of metals in the AFLOW database. So we looked at just the metals, and we said, well, as we increase the number of species, what is the enthalpy gain on average? And so you can see there's a trend that basically the enthalpy gain is declining substantially, actually. And so we start off with a high cohesive energy, and there's 100% of the elements that we studied do form single phase systems. Okay, then we go to binaries, and we see that we drop off to something on the order of MeV per atom, and not all systems form mixtures. Okay, in some cases, this system here is going to be higher than the tie line of the 2 components. So only 59% of those survive, if you will. And we can go on to ternaries and quaternaries and so on and so forth. And so by quaternaries, you see it's very small, the enthalpy gain, on average, as you look across all the systems. Now we can compare this to the entropy, okay? And so the ideal disorder, which is modeled based on the concentration. And so we look at the concentration of the system, and for binaries, it's the ideal entropy is going to be maximum at a 50-50 concentration. That's where you have the most amount of ways that you can mix the system and form different configurations. And so if you assume complete disorder, that's the concept where all of the sites in the crystal can be partially occupied. You can look at it from that perspective, or you can do this game where you have what's called the sublattice. And so sublattice is important from Rico's discussion yesterday, because we had these systems that have both metal components and non-metals. Okay, and so we can think of adding disorder just to the non-metal sites. Okay, and so that's what it means to have disorder on a particular sublattice of the full structure. Okay, and so we look at all these trends, and basically the dashed line here is really the point of comparison here. Here's the n-1 to n entropy gained, and we can compare that to the enthalpy gain. And really the most important factor here is that around 3 or 4 species, the entropy gain overtakes the enthalpy gain. Okay, and so that means that as you increase the number of species, the entropy is going to become more and more important. I think this is kind of a natural consequence of just what entropy is. But so what does that mean? That means that as we continue studying more and more complicated systems with more and more components, which is certainly where we're heading in the future, just multi-component systems in general, entropy is going to be more and more important. And it already starts to become important with ternaries and quaternaries and so on and so forth. And so it's not something that we can continue to disregard in what we model. We have to start modeling it when we're modeling these types of materials. Okay, so how do we study disorder traditionally? There are a few approaches. I've taken some of the most popular ones. There are mean field approaches, and then there's a supercell approach. So under the mean field approaches, we have approximations like the coherent potential approximation or the virtual crystal approximation. Roughly speaking, you can imagine that if you have a site that is partially occupied by 2 occupants or 3 or the like, that instead of the way you might model it is you might make a new fake atom that has the average properties of the elements that occupy it. Okay, and so the caveat there is that they all have to be pretty similar. If the components start to vary at a single site, if you have many components and if their like electronic structure is very different, you're going to have issues with the approach. And the problem is that with this sort of mean field approach, we're looking at sort of an average of the sites. You're going to disregard the effects of lattice distortions. Okay, so you can imagine that if you have this cell and you have one component that is very small, so maybe we start at the beginning of the periodic table and we have a site that is occupied by a very small occupant. I don't know, say something from the beginning of the periodic table, aluminum, let's say. And then at the same site, you partially occupy with something like gold, and it's much bigger. Okay, what you're going to end up having is actually a very important phenomena that we want to take advantage of is what's called lattice distortions. So we have this big element next to these small ones, and it's going to distort and warp the lattice. And these effects are actually going to drive a hardness in the material. This is something that we observe. And so these effects of the local lattice distortions are actually very important from an engineering perspective that is not captured by the mean field approaches. So we're going to disregard those. Now the supercell approach. So we have a very popular approach called SQS. And in SQS, what we do is that we model the system as a supercell. Okay, and so if we have a site that's and I'll elaborate this with pictures in a second, but if we have a structure that has a site that's partially occupied by 2 occupants, you can imagine representing that as a supercell of 2. And so where one of the cells has 1 occupant and the other one has the other occupant that it occupies, and that's sort of and we can model that. We can model that with supercells. Okay, so so with supercells, and so what's the issue with this approach, this single supercell approach? Well, we're going to need to have a very large cell in general to occupy however number of sites that we have that are partially occupied, and the sites need to be commensurate. I'll highlight that in a few slides. But in general, the cells are going to need to be very large. They're going to be very low symmetry, and with the low symmetry, these like the tag that we had, the ISIM tag in VASP that I showed you, which leverages the symmetry of the structure. You're not going to be able to use it, and so the calculations become that much more expensive, and they're that much bigger. And there's an implicit assumption with SQS, with using a single supercell, that you choose only the most random one. And that's a problem because we don't necessarily know how much randomness we want to incorporate into the structure. Okay, so so we have a new approach, and it's going to come from this picture that I keep alluding to. So in a crystal, we can imagine if we had X-ray vision and we can directly analyze the structure of the crystal. Well, we're going to see something like this: repeating units. Okay, and as we look everywhere around the crystal, we're going to see the exact same structure because it's periodic. That's the assumption of the crystal. Now, if I start to dope it, let's say in this case I dope this system with magnesium, and I use my X-ray vision again. Well, at a particular spot, I might see the same structure I saw before. But now, as you look around, you're going to see that actually there's going to be some sites that are going to be occupied with magnesium, and some sites that are going to be occupied by zinc now. And so that's the picture. I want you to imagine that we now have, you can think of it as having sort of pockets of these structures, okay? And so here's another example. We have a zinc sulfur selenium system. I showed this one earlier. Okay, so the primitive cell has 2 atoms, and you have an atom here that's partially occupied by sulfur and selenium in this ratio. Okay, so you can imagine if we want to build a supercell to model this concentration exactly, well, based on the stoichiometry, we're going to need a supercell of 4. Okay, and there's going to be quite a number of structures that we can enumerate using this particular lattice and this construction, this having this site partially occupied between sulfur and selenium. And there's a number of different supercells that we have to look at. I'll show you some pictures of that later, but basically you get a set of structures, and not all of these structures are unique. And so of the set that we get that we can enumerate, for this example, we only have 7 that are unique. Okay, and each of these 7 is going to have its own properties that we can model using all of the tools that we carry from the past presentations. So this is all these structures are going to have their own individual energies and all their own individual properties. And so you can imagine now in the direction we're going. We're going to do averages. Okay, so the concept here is that we're going to model a disordered system as an ensemble average of ordered representative structures. Okay, and we're going to perform averages with each one having a weight. Okay, so each one of these is going to have a unique weight that is associated with the, okay, so let's break down what the weight is here. It's based on Boltzmann statistics, but there's a few components that go into what the weight is for each one of these each one of these representative ordered structures. There's the degeneracy. Okay, so I said that there was not all of the structures that we can enumerate are unique. And so let's say of the full set that there's 5 structures that map and are equivalent to structure 1. Okay, so the degeneracy here is going to be 5. And there might be 7 that map to 2, so that's going to be 7. And in here we have an exponential term. This follows Boltzmann statistics. And this term here is dependent on the energy of the system, okay? So the point is that we're going to skew our statistics to the ground state system, okay? And so that's what we have here. We have basically a difference of the energy. So of these 7, one of these is going to have the lowest energy of the set, okay? So let's say it's structure 7. That's what we're going to call the ground state structure here. And so when we're doing these probabilities to figure out the weights, we're going to take the difference of this structure from 7 and this structure from 7. That's what this term here is telling you. Okay, so it's telling you how far you are from the ground state structure. And this is going to be weighted by a temperature a parameter that we're going to roughly call temperature. And so what is this T telling us? It's really a disorder tuning parameter. Okay, so I'll tell you what happens at the extremes. As T tends to 0, you're really sort of focusing your statistics. You're really weighting it on just the ground state structure. Okay, so all the weights on these guys at about 0 temperature is going to be 0, and the weighting on this one is going to be 1. It's going to, and if you go at the other extreme as you approach T goes to infinity, they're all going to have an equal weighting of 1/7. Okay, so that's how the statistics work. So they're all considered equally probable. Okay, so it's how much disorder we want to incorporate, where disorder is relevant to non-ground state structures, if you will. Okay, so now let's do a comparison. So this is what we call a Supercells approach, and so we're going to compare it to the SQS approach that's very well used, and it's definitely relevant for the structure for some of the analyses that have been formed in the literature. One second. What are the properties that didn't change between the original and the derivatives? Yes, the concentration does not change. So if you look at the stoichiometry of this system, it's a good question. So if you look at the stoichiometry of the system, you see that you get 3 of the selenium and 1 of the sulfur. So it's matching the concentration of the system. And the other thing that doesn't change, it's a good question, is the lattice, okay? So we are actually keeping the lattice of the original structure. Okay, so remember what I mean by lattice is this infinite repetition of points. And so I'm making a supercell, and so the symmetry at some level of the lattice is preserved. But now remember, David talked about this concept of crystal symmetry. So there's a symmetry that there's going to be a concept of the symmetry that's broken by the occupants. And so these structures, while they have the same lattice symmetry, they're going to have much lower crystal symmetry because they're going to have occupants that are not the same anymore. So that is an important distinction relative to the symmetry of the structure. So the lattice symmetry stays the same, and the concentration stays the same from the original and now the derivative. Yeah, perfect. So okay, so we're going to compare POCC and SQS, and the idea is that both of them, as you increase the size and the number of structures that you're using to model them, if you tend to infinity on both in both of these extremes, on both of these axes, you're going to model a disordered system perfectly. Okay, so you have to go to infinity in both extremes. Now, how do the point is that these two approaches do it differently. So SQS does it from one extreme, and really it's doing it by having one single supercell, and you're making it much bigger with every, and the point is that you can model it better by making that one supercell bigger and bigger and bigger until you have, you know, a macroscopic supercell, if you will, that approaches the disordered system you're modeling. The POCC structure or approach does it differently in that we create, we're doing it from a numbers perspective. So we create more smaller representative supercells. So we're creating a set. Okay, and so as we increase, if we want to get more and more accurate, we need to increase the size of the set. We're going to increase, of course, the size of the ordered structures as well. But the point is that they're much smaller than what you would be looking at for SQS. Okay, and so SQS has this concept of approaching it from an ideal disorder perspective. It only has one supercell. Okay, and this really only happens at infinite temperature. And so SQS is intrinsically an infinite temperature solution. Okay, and so you're not going to get you're not going to be able to model phase transitions. You're not going to be able to model precursors. So as you go from this transition of having an ordered structure to a disordered structure, you're basically going to have precursors of the ordered structures existing in the crystal until they all start to form into a single phase. You won't be able to model that with, say, SQS structure unless you go to really large extremes. And so the concept here is that POCC so SQS is really, so POCC is a superset of SQS in terms of modeling. It encompasses SQS and can do more. And from a practical perspective, remember, this is very important. We're modeling these systems. We also need to be worried about the computers are running this. How is the calculation going to look? So the fact that we have smaller cells that we can now parallelize across multiple computers, that's definitely a benefit. It is much more difficult to model one supercell that's very large than to have, you know, so let's say we have a supercell size of 5. It's much harder to do that one big supercell than to have 5 smaller cells that you can put on different computers. And so this is going to depend on your architect and your resources, the architecture of your computer. But in general, it's better to have smaller cells to model, okay, and then perform an average at the end. Okay, so let's go into some of the calculation details. What do we have? So here we have a complicated toy example just to illustrate what we're doing here. I'm going to be discussing things in terms of, this is a generalization of the post-car structure. So we've been dealing with the vast post-car, and we've created a part car, which is for the, you know, partial occupation system. So this input file that AFLOW understands. So what does the disorder structure look like? So we have this site in the middle that is partially occupied between silver and zirconium, and so you're gonna have, if you look at the concentrations here, at this single site you're gonna have more of silver than you're gonna have of zirconium. Okay, and then you have another site which is partially occupied between cadmium and a vacancy. Okay, so there's more of the cadmium than there is of the vacancy. Okay, and so this, by just looking at the numbers of the way that it's partially occupied, you have numbers like 0.733, 0.267 out of, you have to look at that out of 1,000. And so this is, if you're just looking at it based on concentration, you're going to think, okay, this you need to model with a supercell size of 1,000, and that has 16,000 atoms each. That's just one structure, and we're going to make many of them. That's the way we're going to build it. So it's going to be, it's really not something that you can model very easy just looking at the concentration here. So what is the algorithm doing? The AFLOW-POCC algorithm. So we're going to iterate, increasing the supercell size and analyzing the errors that we have at the current supercell size compared to the system we want to model, okay? So we're going to start off with a supercell size of 1, so that's just the cell we start off with. And so based on the concentrations, remember, let's just focus on this single site in the middle. We had silver and zirconium, where silver had the bigger occupation, okay? So if we want to model this system with a single supercell, a single supercell size of 1, the best way to do it is to fill that site with silver, because the error of that site is going to be the missed concentration of the zirconium. Okay, so you can see that here. We have an error of that one site, and that's the concentration of the zirconium that we're missing because we don't have any zirconium at that site. Okay. And so there's two types of errors you can look at it. There's the error associated at the site, and then now there's an error in the stoichiometry. So there's a big error in the stoichiometry. It's equivalent here to the error of the site because we don't have any zirconium. And so there's an error associated with the stoichiometry that we're now missing the zirconium entirely. So there's two errors there, and we're basically going to measure the error of the overall structure with the errors, with the maximum error of all the sites. Okay, so we can do the same thing for the cadmium. The cadmium had a bigger occupancy than the vacancy. Okay, so it's 0.8 versus 0.2. So the best thing to do in terms of modeling it with supercell size of 1 is to fill it with a cadmium. So now we're missing the vacancy, and that's the error. It's 0.2. So the error for this entire supercell model is the maximum number. It's 0.267. Okay, that's just the metric we're going to use. Now we go to supercell size 2. Okay, and so we can now actually occupy that single site of silver and zirconium. We can take one to have silver and one to have zirconium. Okay, and so if you look at the errors of the site, now you're actually decreasing the errors, okay, associated with how much you're missing at any particular site. Okay, and you can do the same thing for the cadmium. And so now, anyway, the point is that you see that the error is starting to drop off as we increase the supercell size. Okay, so now we can start to accommodate for more types of occupants. Okay, so we can increase to a supercell size of 3, do the same analysis, and you see here the trend is that the error is dropping. And you can keep going, and you see that at supercell size 15, we've actually reached, we were able to model the system exactly. Okay, so to the stoichiometry and the concentration at each of the sites matches that of the model that we want. Okay, so we only need a supercell size of 15 to do it, not 1,000. Okay, so we can do it at N15. Now, why is this analysis have any merit aside from just reaching exact stoichiometry? Well, it does, because if you look at the individual errors, you can see that we actually have a nice minimum at about 4. So instead of having to go to a supercell size of 15, maybe that's too big. Maybe we can't model that because of the computers we have. Maybe n equals 4 is something that we can do. And so if we accept that amount of error in terms of tolerance, then it's something that we can do with our model. Maybe our system is stable over a wide range of compositions. And so this is an acceptable amount of error to have in our calculation. And so it might be a good alternative. Okay, so once we fixed the supercell size, now we have to analyze all of the different supercells that we can create. So you can imagine that a single box here in our picture is in a 2D example. This is this is our primitive cell. Okay. Now, how many different ways can we make a supercell size of 4? Okay, so that's the question here. So these are all the different representations of a supercell of size 4. Okay, so we have to look at all of these. And the unique way of enumerating them is called the Hermite nomorpho matrices. Okay, and so if you follow the procedure of this algorithm, it will enumerate exactly the unique set. Okay, and so you can see here that for instance, the yellow and the red are identical, even though they, one of them is rotated with respect to the other. So you have to do this analysis of figuring out which ones are the unique ones. This is the way that you iterate the algorithm. It comes from group theory. Okay, so to identify the duplicates, so now we have our supercell. Sorry, we have our superstructure, and now we have to go about enumerating all of the decorations. So if we have a supercell size of 4 here, we need to take all the sites, and now we need to occupy the partially occupied sites with each of the occupants. And so there's ways of enumerating where at one site you might have one occupant, and at another site you might have the other, the same way we did in the slide before. And so we need to create all of those different decorations that are that are possible through the stoichiometry and the site concentrations. So there's going to be many of them, okay? But not all of them are unique. And so we need to identify the duplicates, and that's going to determine our degeneracy value. Remember that G from that probability. But to do so, it requires analyzing the symmetry of each structure, and that's very expensive. So we've taken an approximation to how to identify duplicates. That's called the universal force field method. So what we do is, this method basically takes a structure and it calculates an approximate energy associated with what's bonded to what are the sites occupied with, and what's the geometry of the system. Okay, so it's a very fast way to get a pseudo energy out of it. Basically, you take one of these structures, you apply the universal force field, and it gives you an energy value. Okay, so this energy value, it's not very good at predicting, let's say, the exact energy from DFT. DFT is always going to give you a more exact energy. But what the universal force field method does very well is that if you have an energy for all of the, let's say we have all of these systems here, we have an energy 1, energy 2, energy 3, and energy 4. These numbers, these values we get from the universal force field, they will tell us which ones are duplicates. So we're going to see that the energy of 1 and the energy of 4 are identical. So now we can identify these as duplicates. So it's very good at approximating at modeling which ones are duplicates. And now that we have the unique set, that we don't have to model the full set, we can now pass the unique ones to AFLOW to process for their properties, just as we've been doing with all the tools that we have amassed from the previous lectures. And we can get the properties of each individual structure. Once we have these properties, we're going to associate a weight with each of the representative superstructures, and then we can calculate ensemble average properties. So for each structure, let's say we look at the density of states. Okay, so each structure is going to have its own density of states, and we can average all of those density of states with the weighting of each of the structures. Okay, and we can play this game with the band gap too. We can do the same thing for the band gap and the magnetic moments. Okay, and in general, you can do this for all of the properties of the structure that we can average in this way. Okay, so now we're going to do some examples together. So if everyone can go to their browser and go to AFLOW, we're going to play with this model online. So if you scroll down, you're going to go to AFLOW-Online, and you're going to click on that. Make it bigger. Okay. And so I think we mentioned the AFLOW-Online in previous lectures, but there's ways of doing, you can come here and you can play with different AFLOW, we can play with different calculations of AFLOW. You can calculate the symmetry, you can reduce the structure input just here on the website, and you can hit submit and it'll process the calculation for you. We can do the same with the partial occupied system. So if you click from input postcard to input part car, we have an example part car here, okay? And so remember, this looks just like a postcard. This is just a long comments line. I'm gonna delete that so it's not confusing. We don't have the wrap on here. So this is a comment line just from the postcard. Here we have the lattice, the scaling factor just as usual, and we have 2 new numbers here now. These are associated with the errors in site and the tolerance in the sites and the tolerance in the stoichiometry. For now, we're not going to worry too much about the distinction. We're just going to say that we basically want to model the system more or less exactly. So we're going to put a very tight tolerance around the errors that we want in the site and in the stoichiometry. We have our lattice vectors here. And this line here used to be just a single number. We used to have like 1 or 2 or whatever. But now with partially occupied systems, we're going to have a fraction. So here we're reading, we have 1 times 1. So this first site here is going to be fully occupied. And then we have 1 times 0.5. So the second site here is partially occupied. And you can see that it's going to be a partially occupied with the third site here. So they're going to have the exact same coordinates. Okay, so you see that they sit at the exact same site. And one of them is partially occupied with, and the site is partially occupied between hafnium and niobium. Okay. All right. So we have our input part card. We're going to scroll down. We're going to go past all of these different calculation types, and we're going to go to the partial occupation tools, and we're going to click on the first button here, optimize Hermite normal form supercell size. Once we click on that, I'm going to hit submit. And it's processing the calculation. Okay. So this is the output of the calculation. So it's quite verbose. It's basically going to spit out the input you gave it, and it's going to do some analysis. We're going to keep scrolling down. It's going to do a symmetry analysis on the backbone structure. This is what we're going to call the parent structure. So the parent structure is basically the backbone structure. So remember, we started from a particular primitive lattice, and then we've partially occupied the site. So this is the parent lattice structure here, okay? And we're going to perform a symmetry analysis on that structure to understand what the symmetry is. We're going to scroll down. It's very verbose. And now we're going to, okay, so now we come back to the POCC calculation. So now it's going to calculate what the H&F value is, given these particular tolerances as inputs. And now we want to know what the optimized H&F value is. So basically, what supercell size do we need to model the system to within our tolerances? And so here we have this table, as I showed you in the slides. And we're going to start with a supercell size of 1, and then we get to 2. And because we only have one site that's partially occupied between 2 occupants, it's pretty clear that we only need a supercell size of 2 to model the system. Okay, so this is just to get the super lattice size. Okay, so we're going to go back up, and we're going to submit a new calculation. I want to see what are the representative ordered supercells. Okay, so now with a supercell size of 2, what are the different ordered structures that I need to do the unique ones? So I'm going to hit submit. Okay, and so we're gonna scroll down. It's got a lot of the same output, the symmetry analysis. Okay, so it does the same calculation. It gets an optimized H&F value too, and now it keeps going. So so now that we have our super lattice, we have to create all the different supercell decorations. We need to get unique counts. So we get a unique count of H&F matrices. So there's 2 unique H&F matrices that are going to create these super lattices. And then there are 4 supercells that we can there are 4 different supercell decorations that we can make with all of these different combinations or permutations. And now of these 4, we're going to do an analysis of the pseudo energies of each of these decorations. And we see that of these, only 2 are unique, okay? And so it gives you the pseudo energy for each. This is the energy calculated by the UFF approach. And it even gives you the degeneracy associated. So each one of them carries 2 structures associated with it, okay? And then we print out the structures. So these are perfectly good postcards that we can now put into AFLOW or into VASP directly and actually get the properties of these structures, okay? And so you can see that the last 2 sites are a little different from each other. So this has 0.5, 0.5, 0.25. This has 0.5, 0.50, and so that's where you expect the difference to be because the carbon is fully occupied, okay? So that's how we model it. All right, anyone have any questions about how that works? Good question. So why didn't we use Xtel Finder to find duplicate structures? That's actually an option. So we can use Xtel Finder to find the duplicate structures, and that is an option through the through AFLOW. In fact, I think let me see if I can show you this in the portal. It's actually something that we can modify in our AFLOW RC. Okay, so if we want to look for the AFLOW RC, there's one that we have in the on the machine. So if we remember, David went through what the AFLOW RC looks like, and you can actually turn this on. So if we go down to POCC settings, there's actually a setting to turn this on, and let me see where it is. Here it is. So we can actually perform the robust structure comparison and use Xtel. Yes, Xtel is for ordered structures, but we can use, so once we make the full set of ordered structures, now we can reduce to the ones that are unique based on Xtel Finder. Now the reason that this default is turned off is because we're going to be dealing with numbers in general that are very large. We've enumerated structures that give you hundreds of thousands of different ordered configurations, okay? And the UFF approximation is going to be, in general, much faster. Now, it's not going to be as accurate as Xtel Finder. Xtel Finder will tell you exactly which ones are unique and which ones are not. And so we have to accept that if we want to do this analysis in somewhat of a real time, we need to use this approximation. Now, in the future, we're going to be able to incorporate. So David's done a good job of parallelizing the code, and so we can actually, if we want to get the exact number, parallelizing it, maybe even across different machines, we can actually speed it up in that regard. But again, we're still using a lot more resources than we would if we just did the approximation. So that's why we don't use Xtel Finder by default. But if you're concerned that the UFF approach is not giving you the right answers, then you're going to want to turn this on, and it'll give you the exact duplicity of all of the structures. Okay. So does that make sense there? Why we can actually use Xtel Finder here for the ordered structures? Can you explain again the way you determine the error for the different supercells? Sure. Okay, so we're going to go back up to this slide. No, this one. Okay, so the error. So okay, so for this first system, okay, so remember so remember this system. This is the numbers that we're working with. So we're working with silver having 0.733. Okay, at this site here. Okay, this particularly partially occupied site. This site's going to have, as you can see here, it's going to have 0.73% occupied with silver, and it's going to have a 0.267 concentration of zirconium. Okay, so those are the concentration ratios. Okay, and so this slide just focuses on the site error. Okay, I'm not looking at the stoichiometry error, which is another parameter. We can look at that in the output of the AFLOW-Online. But this picture just shows you the site error, and that's really what I want you to just imagine, that we're doing this analysis per the sites. So if we want to model our system using a supercell size of 1, that's our input structure, then this site here, which should be partially occupied between silver and zirconium, the best way to model this system with just a supercell size of 1 is to put the dominant occupants. Okay, so silver had 0.733 versus the zirconium, which has 267. So we're going to fill that site with silver. Okay. Now, I asked the question, what is the error of this supercell as a representation to our disordered system? So the error that's associated with this one site is the error of the zirconium that we're missing. Okay, So there's error, the concentration of zirconium that's not present in the system. You see here that at this site, we don't have any zirconium. So the error is 0.267, okay, for that single site. And we can play the same game with the cadmium. Cadmium at this site. We had a vacancy of concentration 0.2 and cadmium of concentration 0.8 in the system that we want to model. So we're going to, if we want to model with one supercell, the best way to do it is to fill it with cadmium, because that's going to give us the lowest error. So the error of filling it with cadmium is now the concentration of what we missed instead by not putting a vacancy, which is 0.2. Okay, does that make sense? And we can play this game going forward. So now we can do it with a supercell size of 2. So now with 2, we can actually occupy one with silver and one of the middle sites. You can imagine that this is the breaking line between the perimeter structures of the supercell. So here we have our cell 1, and here we have our cell 2. And so right here we can put a silver here, and then the next one we can put zirconium. So at this one site, okay, we can do we're basically measuring what is the error of this particular site of not putting from our model system. Okay, so by having this full structure here. Okay, so at this particular site, and so the error is dropping as we increase the supercell size. Okay, and so now we get an error. We have to average over the 2 sites. So now we get an error of 0.233 effectively. Okay, and so we're going to do the same thing for the cadmium. And again, the best strategy for having a supercell size of 2 is actually to have the cadmium in both. Okay, so the algorithm is doing this analysis for you. It's telling you that the best way to do it is actually to have a cadmium in both. Once we get to a supercell size of 8, okay, now we can start to put, or actually 5. Once we get to 5, we can actually have one of these cells filled with well, not filled, it's going to have a vacancy. Once we get to 5, we can actually start to model a vacancy because the concentration is 0.2. Okay. Yes, the error is based on the ability to incorporate the true composition. That's exactly right. Okay. And so it's very tricky bookkeeping, but you leave that to the algorithm to do. Yeah, no problem. And let me know if that wasn't clear for anybody. We can go over it. Okay, so let's keep going. So we covered how to do it online. All right, so now we have a short exercise that we're going to go through together. Well, not together. We're going to go into our small groups. So I'll explain the exercise, and then we'll break off into our breakout rooms. So I want you to go to the AFLOW-Online, and I want you to modify the part car. So I want you to play with it, and I want you to create a 5 metal carbide. Okay, so we had a 2 metal carbide before. I want you to change the composition, change the part car, and now create a 5 metal part car. Okay, and then I want you to run the analysis and figure out how many derivative structures you have. Okay, so now we'll go ahead and we're going to go to our breakout rooms. All right, looks like we're starting to come back. I will show you how to do it. It's pretty simple, pretty quick. I'll start fresh. Let me share my screen. All right, so I'll start fresh. 1 second. So from the AFLOW website, from the AFLOW website, we'll go to AFLOW-Online, the input part car. So the lines we really need to change are this line and these lines. Okay. So if we want a 5 metal carbide with 0.2 concentration on all the metals, then we're going to make this 0.2 and 0.2, and I'm going to repeat this for 5 times. Okay. So now we have 1 and then 5 of these 0.2s, and then I'm going to make copies of these lines. So everything past this number, so all of this here, the carbon, what the elements are, these are all comment lines, so you don't need to change them, but for the sake of having something that looks semantic, I'm going to change them for what we're doing here. But all we really need to do is just have this, so have the coordinates correct. So now we have 5 of these identical lines here, okay? But I'll change these lines here too so you can see just what it is. So we have tantalum, and then we have vanadium and tungsten, okay? Then we scroll down, we generate the structures. And you can see we have our usual output, all the symmetry and everything. And this is the line we were looking for. We have 49 unique structures for this system, okay? Or this one, calculated 49 unique supercells. All right, so I hope everybody was able to get it. Does anyone have any questions? Let me get my chat up. 1 second. Okay, so if there are no questions, I'll keep going. All right, so let's keep going with the presentation. So, oops. All right, so now we can actually start to use the command line for this. So I'll show you, I'm going to show you the different commands, and then we're going to have some exercises, okay, at the end. So I just wanted to check that that's what's going on. Okay, so we're going to have, let me show you all of the different commands, and then we'll break out into groups again. So, all right, so we can actually use the command line for this, and we're going to start by we're going to build it step by step, okay? So first, we're going to start with a command that we would have run yesterday with David. So this is for the rock salt structure. This is the underlying structure to the system we were just playing with. Okay, so the underlying structure to this 5-metal carbide or the 2-metal carbide was a rock salt structure. So we're going to use the ANRL designation. So we have AFLOW Proto, and we have this designation, and I don't need to specify this, but for the sake of completeness, we have params equals -1, which means just give me the recommended scaling factor given Vergard's law, okay? So we get a system that looks like this, okay? So this is how you want to start. You want to first build your ordered structure, and then you're going to add the POCC params on top of it, okay? So, I want to make a distinction here very clear, and so I'm going to make this especially clear in a few slides, but there's something I want you to notice about this system that with the way that I'm going to talk about the nomenclature. So this system here has 2 species, A and B. Okay, so those are 2 species. That's the way I'm going to call them, and it has 2 site positions. Okay, so make a distinction between the fact that you have 2 sites and you have 2 species. You might also have 2 species, but where you have a bunch of A's, okay? And I'll show you an example about with that in a few slides. But that's a distinction I want you to make. So to construct the 5-metal carbide from the base rock salt structure, we're gonna run AFLOW Proto. Everything is the same up to here. So this is the prototype command, the prototype label. And now we have 5 metals, okay? So we need to put our 5 metals in alphabetic order, okay? So all colon separated. We have our params, which we really don't need, but we put there for completeness. And then we have our POCC params. Okay, so now what's going on with the POCC params? Very long, kind of complicated string, but I'm gonna break it down for you. We have, so here we have our species in alphabetic order. We have, okay, so we're going to specify our 0th position is fully occupied, okay? And, okay, so here I can show you with reference to what the actual system is going to look like. Let me move these 2 things here. Okay, so we had our first site. Remember, in the original rock salt structure, we had 2 sites where we had A and B. And so we're going to so we want the first position to be fully occupied. So P0, that's position 0. And then with a hyphen, we're going to specify 1 times A. So that's really this scaling parameter here. Okay. And then I'm going to put an underscore. Don't worry, you're going to be able to copy it from the slide you have, but we're going to put an underscore here. And then you're going to specify for position 1 of the original rock salt structure, how you're going to break it down. So position 1, and then everything else is separated by hyphens here. Okay, so look at all the hyphens, and you're going to do 0.2 times B, where A, B, C, D, E, F refers to the order that we have here. So this is A, this is B, this is C, D, E, and F, okay? So it is a lot packed into one command, but we're going to show you the power of being able to specify it this way. So we have position 1 that is specified by 0.2 times B. So we're kind of following this line here. So 0.2 times B, 0.2 times C, 0.2 times D, 0.2 times E, and 0.2 times F. And it creates this structure here. Okay. So this is the proto command. This is just to spit out the part car. Okay. And now we can use this nice bash feature, this pipe. So we take that same command we had before and we pipe it back into AFLOW. So AFLOW is going to read the part car input, and we use the tag --H and F. We're going to get the output we saw on the website. Okay, so we're going to see all the symmetry stuff above, right? And then we're going to get to the bottom of the output, and we're going to see the tolerance value, the site, stoichiometry tolerance, the site tolerance, and then the optimized H and F value. Okay. Where it's going to print out the table, okay, the same table we saw online, but now we have more, we have a much longer line because we have more occupants to look at, and then we see an optimized value of 5. So our supercell size needs to be 5 to model the system to within the tolerances we specified, okay. And then you can run the --H and F cell command, and this is going to give you the output that we saw for the second button online, which is all of the unique ordered structures, okay? So you're basically going to get an output where it tells you, okay, you have 49 unique structures, and then here is structure 1, and then we look down structure 2, structure 3, structure 4, okay? So that's how you use it at the command line, and that's really all that the website's doing. It's just leveraging these commands. Okay, so now instead of the proto command, we're going to use the AFLOW Proto command, and we're going to be able to do a lot more with this because it's going to create individual input files for AFLOW. Okay, so now instead of Proto, we're going to have AFLOW Proto. We have the same specification here, the same POCC parameters, and we're going to run it with ---- generate AFLOW in only. And what you're going to see is that it's going to create all of the input files. So this one, I'm actually going to run on the line so you can see what's going on. I'm going to run in the terminal. Okay, so let me make this smaller. And I'll keep this here. Close this. Okay. So this one I'm going to play with here. So we're going to go to day 3 here and scratch. And I'm going to open up a terminal. Okay, so we're going to do module load AFLOW. And just for completeness, I'm going to run the other commands I had. So first, I'm going to create the part car on the command line. So I'm going to paste it here. Okay. So I'm going to hit paste. And you see that AFLOW creates. Oh, come on. AFLOW creates, 1 second. AFLOW is going to create the part car. Okay. So here we have the part car, and you can see that it created it with the site that's partially occupied by 5 metals. Okay. So now we can take that command, the same command. So I'm just going to tap up with the up arrow, and I'm going to type AFLOW --H and F. Okay. And now we're going to see all this output that we saw on the website. And you see that it written here in green is the 5 value. So we need a supercell size of 5 to model the system to within the tolerance values that we provided. I'm going to hit up again. And instead of H and F cell, instead of H and F, I'm going to type H and F cell. And I'll hit enter. And it's going to go through the same procedure, get the H and F value. And now it's printing out all of the unique structures. Okay, so we saw a bunch of structures one after another, and these are all 49 structures. Okay, all right, so that's running it with the proto command. This is just spitting everything out to the command line. Now I actually want to create files, so I'm going to delete that pipe and I'm going to go here. Let me make this a little bigger just in case you guys can't see. Okay. And I'm going to type AFLOW Proto here. Oh, and I forgot to add the generate AFLOW only. I'm going to type generate AFLOW only. Okay. So same command, except for the proto stuff. We're going to write AFLOW Proto, the proto tag, and -- generate AFLOW only. Okay. And I'm going to hit enter. And I now get this output that it created in AFLOW. Okay. So we're going to go to our browser here, and you see, okay, now we have a new AFLOW, we have a new directory. We're going to go inside. It's got a few layers. Let me describe the layers very quickly. The first layer, just like our database, has the chemistry, okay? So it has the pseudopotentials here, back to back, and it even specifies that it's run with a POCC calculation. That's just the default for AFLOW. And then the second layer is our prototype designation. So instead of just having the rock salt here, which we would have had otherwise, the prototype designation now tags on the POCC params. Okay, so you see this is what we wrote on the command line. Okay, that's now our prototype. Okay, and now we have a new AFLOW in, and this AFLOW in again automatically generated. And I'm going to can I do a zoom in? That's okay. I don't know if I can zoom in here. Oh, this one, right? No, I don't think so. Okay, well, the point is that we basically have a normal AFLOW in, and instead of a postcar, we're going to have this side a little bit. We're going to have now the part car where the postcar would have been. Okay, so you can't just run this. You can't just take this particular file and put it as a postcard because VASP is going to crash. It's not going to know how to read these partial occupations. Only AFLOW understands this. So you run this through AFLOW and it's going to generate all the input files. And I'm going to show you how to do that. So now we have a part car inside of the AFLOW in. The other thing to notice is it added this tag here, AFLOW-POCC calculate. Okay, so it did all that automatically. You don't have to worry about that. Just understand that that's what the structure is and how it's built. So from the command line, I'm actually going to open up a new terminal here, just so we don't have to do the CDing. Module load AFLOW. Okay, so you see that I'm inside. Let me make this zoom in. Zoom in. So now we have our AFLOW in. This over. Okay, so now we have our AFLOW in. Let me make this a little bigger so you guys can see. Okay. So now we have our single file AFLOW in. So I'm going to run this. AFLOW -- run -- generate AFLOW in only. Okay. And it's going to write out a big file. So it's going to take a second because it's basically going to write a file that's going to contain all of the permutations that we get with our decorations. And if you look up here, there are, so that just to give you an example of what's going on, we had 49 unique structures. Okay, so that's the number I want you to remember. We had 49 unique structures, but the total set of structures that we can make, all the total configurations, there are 600 of them. Okay, and I'll show you inside when we get to the AFLOW in, there are 600 of them. All of the 49 of them, except for one, have a degeneracy value of 10. And then the very last one has a degeneracy value of 120. So basically of the 600, most of them can be mapped. Most of them, you can think of them as groups of 10, where 10 of them have one unique representative. And then the last one has one unique representative for 120 of the structures. Okay, so you can see that. Let me show you what's in here. So now we run the command. Everything was automatic. I just had to run it. But now we have quite a few files in here. We have some symmetry files. You can see. I'm going to show you. Actually, I'll do it from here from the terminal. So now we have all these files here. All these directories. Basically, we have a new directory, a new run for every single representative ordered structure. So we have A run POCC1 all the way to A run POCC49. Okay, and then the rest of it is a hash. This H3C6 is basically saying that I needed the H&F matrix 4 because we start from 0. H&F matrix enumerated 4. This is just how the algorithm enumerates it. And the site configuration 7. Okay. And if you want to see what these correspond to, I'm going to open up the files and show you. So we have, okay, so we're looking for AFLOW-POCC. Here it is. So here are the matrices. Oh, it's XZ. 1 second. I need to unzip this file because AFLOW automatically zips. So I'm going to XZ minus the star. So that's going to unzip everything that has an XZ in front of it. Okay. And now I'm going to open up the file because I want to show you what's in it. So here's the H&F. No, I got to open it up with gedit. 1 second. Right here. Okay, so opening it up with gedit just to see what the contents of the file are, you can see that we basically have 5 matrices here. So this is the way that it enumerates it. So here I print out 1, 2, 3, 4, 5, but the hash is built starting with 0. So this is the first matrix, the second one, the third one, the fourth one, and the fifth one. These correspond to how we build our superstructure. Okay, and then we're going to look at the file site configurations out. I'm going to open that up with gedit. And now we have everything running from this is the 1 out of 20, 2 out of 20, all the way down to 120 different ways that we can build the structure. So look at what I'm showing here. So look at the 120th one. Okay. I hope you can see. Let me see if zooming in helps. Okay. So I want you to see what we're writing here. Basically, what I'm printing out here is the order in which the elements are going to appear in the postcard. So we're going to have 5 Cs, and then we're going to have the first site occupied with tungsten, then vanadium, then tantalum, niobium, and then molybdenum. Okay, so this is the order that they're going to be enumerated in. And then once those sites are decorated with those elements, AFLOW is going to go ahead and automatically alphabetize them. So it will always show the order as molybdenum first in the postcard. It has to, because it has to be alphabetic. Let me show you an example. So we go inside of 49, and I open this up with gedit. Okay. So we basically have 5 sites that are appearing with carbon. And then it appears in alphabetic order: molybdenum, niobium, tantalum, vanadium, and tungsten. But this is the 120th one. So the sites here are decorated first with the occupants, okay? And then we go ahead and alphabetize them. You don't have to worry about these details. You just have to understand that this is what the algorithm is doing underneath. It's going to create all the structures, and all you have to worry about is now running all of these individual VASP runs. These are now concrete VASP runs that you can run through AFLOW, no problem. Okay, so these are fully encapsulated VASP runs, and then I'll show you in a few slides later that we can actually once each one of these has a VASP run inside, you just hit AFLOW run again, and it'll do the post-processing for you where it calculates the ensemble average properties. Does anyone have any questions up to this point? Nope. Okay. Oh, is this duplicate structure the G term? Exactly. The duplicate. Oh yeah. Actually, great point. Thank you very much for adding me, because I didn't show you that in the AFLOW-in. Actually, this information is printed. Great question. Okay, so yes, what you're saying is exactly right. Oh, let me just, okay, so if you look at the title line here, it's actually printing out a lot of information. This DG here, 120, this is the degeneracy value that we're going to plug into our Boltzmann probability to get the weighting for this particular structure. So this is the last structure in the set. This was the 49th structure. And as I told you, this degeneracy value is 120. So this one's going to have the biggest, because of the degeneracy value, it's going to have a big weight associated with it. But remember that the weighting also incorporates the energy as an exponential, remember. So this, I know that this structure in particular, it's not the ground state. And so there's a balance to the fact that you have degeneracies, but you also have to have the lowest energy to have a good solid weighting to your structure. Okay, so that's going to be a big part of the weighting, is what is the actual energy that VASP gives us for this structure. Is there a way to extract just postcard files? Yes. Oh, you mean the postcard files? Well, if the way I would do it is that I would, it's a good question, and I have to play a little game of bash here, but this is how I would do it. So I hope you're familiar, but yes, you can. And I need to test the command because I don't remember off the top of my head. But basically, I would go about the procedure of, well, but yes, but actually it's even simpler than that, because we do assume that that people want this. But yes, part of what you're saying is correct. One second. So I should be able to do AFLOW minus extract X post car and AFLOW in. And it gives you the thing. So if you just want postcards, what I would do is I would do 4. This is just a little bit of bash. Don't worry about this if this is not your concern, but I'm gonna do this. So a run star do, and then I'm gonna CD into the directory. So push D, I, and then I'm gonna go inside the directory, and then I'm gonna run AFLOW minus X post car, AFLOW in, and then I'm gonna redirect it out to postcard, and then I'm gonna come back out, and then done. So it's gonna run through this process of printing out all the postcards. So it'll take a little bit of time, but now once we go inside, I'm gonna show you that basically now we have an AFLOW in and the postcard. Okay? So it's as easy as that. More or less, that's what AFLOW is doing, is that it's kind of grepping those lines. No problem. Any other questions? Okay. Well, feel free to put them in if you have them. But yeah, I'll keep this running in the background. It's just going to generate all the postcards. All right. So we've gone through all of this stuff. Okay. Now I want to there's an important distinction that I want to draw very clearly for everybody. Okay. So it's this concept of P versus S. Okay. So I'm going to pose the question. I want you to create the same concentration, the same concentration of a 5 metal carbide. Okay, this chemistry here, but using a different prototype tag. Okay, so I show here. I give you the link if you want to take a look here. We can take a look at the structure here if you want. This is cementite. Just an example of structure. Okay, it's one we played with yesterday with that David showed. And so here's the structure. Okay, so my super zoomed in here. All right, so here's the structure, and basically what I want you to notice, I'm going to generate the VASP output, is that we have a bunch of C's and a bunch of F's. Okay, and we have 16 positions. All right, so I want to belabor this point. We have a bunch of C's, a bunch of irons, and we have 16 positions in total. Okay, so in the way I want you to think about it is that we have position 0, position 1, 2, 3, position 4 is the first position for iron, all the way up to position 15. Okay, so keep that in mind. That's what I mean by position. But we have 2 species. Okay, species 0 and species 1. It's a grouping of positions. Okay, so if you wanted to go about building this command line structure using the P designation, as we've done for the rock salt, you're going to have a very, very long command, because you basically have to walk through each position. So I need to say, okay, position 1, give me 1 times A. Position 2, well, I'm doing it position 0, position 1, give me 1 times A, all the way up to position 3. And then we go to position 4, and it's very repetitious, okay? And you're gonna have this big text. and you might make a mistake somewhere, you might type something wrong. So the point is, this is what the P versus S is for. If you remember, this is the input I had for the rock salt structure. So I had P0, 1 times A, and then P1 for the position 1, and then I had that partially occupied with all of these different occupants. It's actually the exact same command for the different label. Okay, so this is why this understanding what a decoration is and what a backbone structure, why this is so powerful, this abstraction, is because I could have done the same command here that I wanted to do up here using a very shorthand, and I'm replacing basically the P with just the S, because I'm now specifying I want the species 0 to be partially occupied with 1 times A, and I want species 2, or species 1 here, to be partially occupied with B, C, D, E, and F. And that's going to give me a very big file. So now I've specified the way that I want to write it here. Okay, so we're basically able to do all of these 16 sites partially occupied in one very short command. Okay, so it's a shortcut. The point is, you can always map back to this positions designation, but the species designation is a very nice shorthand. Okay. All right, and now I want to show some high throughput commands. So we can actually create 56 different combinations of pot cars. So okay, so here's what's interesting. We can actually create. So let's say I wanted to occupy. Remember the designation yesterday of colon versus comma. Okay, so we're using this site specific designation. So every site is designated with a colon, and then the commas separate what I want to make combinations of. So I want C to sit in the first position because alphabetically it comes before all of the metals. And then in the first site, I want to make every combination where hafnium is the first one, then molybdenum is the first one, then niobium is the first one, then tantalum, etc., etc., etc. And then I'm going to do the second site, the same thing. The third site, the same thing. And the POCC parameter stays the same as we had before. I'm writing S here as a shorthand, but since we only have 2 positions, it's the same thing whether I wrote S or P. Okay. So I'm actually going to put this in the command line so we see what is going on. Here we are. All right, so it did it created all the postcards as you asked, Daniel. Okay, so I'm going to delete that because I'm going to create a whole mess of I'm just going to go ahead and delete this directory because we don't need this anymore. And I'm going to paste my command. Paste. Okay, and then we're going to hit enter, and I'm going to show you what it makes. You're going to see a lot of output because AFLOW, this is the power of doing things alphabetically, is that because we specified it alphabetically, AFLOW understands that it's only going to create the unique combinations that are alphabetically ordered. So it's not going to create any duplicates where you've swapped and you really have a duplicate structure. So by doing it alphabetically, you're going to get only the ones that are unique combinations. So you see, there's a few creations, but most of these are non-alphabetic combinations that are really duplicates of another one that's been created. So don't worry too much about the output. Just understand AFLOW, what AFLOW is doing underneath the hood. Okay, so we're going to go. I'm going to open this up with the directory scheme. I'm going to come back out. I'll hit refresh. So I go to Scratch. I walk into AFLOW data. Look now. Previously, I only had one chemistry here. Remember, we had the molybdenum, niobium, tantalum, vanadium, tungsten variants. Now we actually have 56 combinations. So I basically made, this is from a study that we did where we looked at, we looked at 8 different refractory metals, and we wanted to make all the combinations here for these different runs. Okay, so of the 8 refractory metals, how many different 5 metal combinations can we make? So 8 choose 5, you get 56. Okay, so I created all of these with one single command. And each of these it's going to have the same prototype designation inside. And here we have an AFLOW that has a part car. Okay. Oh, it opened it up with Emacs. Wow. I'm not a big Emacs person, but let me, 1 second. Let me open it up with gedit. Okay, so inside here we have an AFLOW that contains a part car, not a post car. So to create all the post cars, we need to go into all of them and run AFLOW again to create the 49 combinations for all of these. Okay, so if I were to do that, we're going to basically get 49 times 56, about 2,000 VAST runs we're able to create more or less with one command. Okay, so this is a very high throughput way of doing this analysis, and that's exactly what we did for the studies. We did this using this single command. Okay, anyone have any questions about this? So we're running a little short on time. The rest of the slides I had were kind of empty. Well, I'm going to go through a few of them. No, actually, I'm going to go through a few of these just to show, but really what I'm going to get to is I want to get to the exercises. So I was going to highlight some of the interesting things about the study that we did, but we're not going to focus on that. I want you guys to actually have practice using this. So I'm going to go through some of the slides here, and then we're going to go back and we're going to run these exercises. Okay. So so I want to show you just some things that you can actually visualize with this architecture, with this framework rather. So you can actually do this analysis, and we have done it for different concentrations. So you see here we have the model system I showed you before. We had a zinc selenium sulfide system, and this system is known to have what's called optical bowing. So as I change the concentration of the selenium, the system is going to have a decrease. It's going to decrease the band gap as we change the concentration, and the relationship of how it decreases is quadratic. You see that it kind of looks like x squared. Okay, so it has this quadratic relationship. It's not really linear, although there are some people that say it's linear. There's some debate there, but the majority, the consensus is that it's basically there's this curvature to how it decreases. And using the POCC Ensemble approach, we're able to actually perform these calculations, and we see that we actually do observe this quadratic dependence, this optical bowing. So you can do this analysis for the band gap, and we did something similar for magnesium zinc oxide structure. And what's interesting is that this has actually been done, the band gap. So as you change the concentration, you actually have a phase transition. You go from wurtzite structure to rock salt. And the system's actually able to model that well. So for the wurtzite, we get a linear relationship. And then for these concentrations where we have a rock salt, you see that we get a jump in the band gap. And so we actually do observe that with the model. So the model is able to predict, and it's got some curvature to it, okay? A little bit. And the model is able to capture it. You can actually observe how the band gap changes and why. Okay, so I've plotted here the density of states at varying concentrations. The one that's really nice to look at is this rock salt structure, this wurtzite rock salt structure, because with the rock salt structure, you actually see that the reason the band gap changes is because you see this big push back of the conduction bands, okay? And so this is how the band gap changes, is that the conduction bands really push forward. And so, so you can actually visualize and see this with this model, okay? And you can actually study magnetic properties too. So you can look at the average magnetic moment. So, so we're looking at this copper iron system, and we're looking at the average magnetic moment as we scan, as we increase the copper concentration. So we know iron is magnetized, copper is not. And so the magnetization decreases, and you see that the calculated values actually model this pretty well, okay? And what's nice is that, I'm going to show you in the next slides, what's nice is that you can actually go beyond modeling it exactly with the right stoichiometry. So remember, for some of the systems, if we have a site where we have 2 occupants, the POCC algorithm is going to tell you to model it with a supercell size of 2, right? You can actually, that's actually a parameter you can change. You can go beyond 2. You can actually create supercell sizes that are supercell size of 4, let's say. And you're going to get more supercells, And so you can actually go beyond what the algorithm tells you. And so that can help you in increasing the accuracy of the calculation. You can see that by going to a supercell size that's even bigger, you can get even better results. Okay. I'm not going to talk too much about the rest of the slides because really what I want to do is get to the exercises. So the other stuff is some of the other studies we've done. I just want to emphasize that I want to emphasize actually running these calculations. So we're going to go ahead and break to our breakout rooms. I'm going to explain the exercises first and then we'll break out. So we're going to create a part car for this magnesium zinc oxide system. This is the system we were just looking at. This is this system here. So we're going to create it. I give you the prototype label, and you don't have to worry about the params because this is the hard-coded prototype designation. You're going to create the part car for the zinc selenium sulfide system. I give you the label, and you don't have to worry about the params for the prototype. Try switching between, you have to figure out how to do it with S versus P. So there's a little trick there. And then you can actually create, with these high throughput commands, you can actually span creating with a single command, you can actually create multiple runs. One where X here spans from 0.1 all the way to 0.9, okay? And your small group leader, if you will help you with that. I give you the labels, everything's there. You just need to create the right POCC params, okay? And then go ahead and try to figure out how many representative structures are for each. All right, so we will go ahead and break out for our breakout rooms now. Hello, everybody. So I'm going to start by, we're going to I'm going to do the last example just very quickly. Just to show you that how we can go about doing this, because this is the most complicated one. And okay, so first you want to start by building the backbone structure. Okay, so you're going to want to start first with the FCC or the BCC structure. The important thing to know is that they only have one site, so that's what makes this one kind of easy. BCC proto equals BCC. Okay, so there we have our designation. And so you're always going to reference the POCC params to what is built out of AFLOW. Okay, so I was explaining this to somebody, brought it up, but if you have the rock salt structure, you know that these two sites are equivalent, the 0 and the 0.5 by symmetry. So these are interchangeable, but whether you occupy the 000 or the 0.5 one, depends on the order in which you have it printing out in AFLOW. So that's how you do 0, 1, 2, 3, based on how it prints out here for that label. So I'm going to print it out very quickly for AFLOW Proto. So how do we do this designation in one? How do we make all these different AFLOWs with just one line? So you do BCC comma FCC because we're doing both. And then I have to put the species in alphabetic order. So CUFE. And then POCC params. Okay, so there's only one site here. Let me move my zoom thing here. There's only one site here, so we only need to worry about one site. So we do P0 underscore, sorry, P0, and then 0. We want to do, sorry, 0.1 times A, and then 0.9 times B. Okay, and then I'm going to put a comma. And then I'm going to copy this and do paste. And we're just going to change 0.1 to 0.2 and then 0.9 to 0.8. And then we're going to keep doing that. Okay, so we do that for 0.25 and so on and so forth. And that's how you build it for this command. You keep going all the way till you get to 0.9. You hit enter and it's going to create all of the different variants you provided it with. Okay. So that's that exercise. The last thing I'm going to show you, I'm just going to show you how it works, is the post-processing. Okay, so we're not going to do this in the breakout room. I'm going to do it. I'm just going to demonstrate it for you here. So I'm going to close all this stuff out. In AFLOW 3, if you go inside of POCC, post-processing, you're going to see that I actually have done the runs for you. Okay, so I did the VAST runs for you, and I give you the outputs here. Okay, so these are only the outputs that you need. You need the outcars, the postcards and some of the output files from AFLOW. Okay, so I did the VASP runs for you, and all I want to show you is how easy it is to do the post-processing. We're not going to wait for it all to finish, but I'm going to open up a terminal from here. I'm going to do module load AFLOW. Okay, and now that we're sitting in this structure here, okay, we don't have a lock file, so I'm going to go ahead and hit AFLOW -- run, and it's going to go ahead and run all of the post-processing, okay? And it's going to take a little bit of time because it has to read all the files and all that. Basically, you're going to get a bunch of output files and a lot of pictures. And so I'm going to let that run in the background, but I just want to show you what you're going to get. You're going to get a bunch of density of states pictures, okay? And so you're going to see that you can actually, I made a little GIF here for you to look at, but the GIF basically spans all the temperature ranges. So you can see how the density of state changes as we change the temperature, okay? And it doesn't change very much. This one doesn't, the density of states does not change very much for this system, okay? And so you can look at it, you can look at the density of states as a function of the orbitals, projected on the orbitals, or you can look at it as projected along the species, okay? And you can see that you get all the different contributions for each of these, okay? So you can let that keep running in the background, and you'll see that it's actually going to create the PNGs for you. Actually, it's the PDFs. It'll create the PDF pictures for you. And then you're going to get an output file. And this output file is going to give you all of the properties that you need. So there's some temperature independent properties. So there's the ground state enthalpy. Okay, so that's which of the 49 structures is the lowest energy structure, and it tells you what the energy is of that structure. So in this case, it's 33. It tells you the mixing enthalpy. Okay, this is a term from one of the studies we did, and also the entropy forming ability. Again, these two parameters come from a study that we did based on these POCC runs that we weren't able to go over. But basically, it prints this information out for you. And then for each temperature, you get a probability for each of the supercells. So what is that Boltzmann weighting, okay, at temperature 0? And then it even gives you the band gap. So this one's a metal, so you're always going to get a band gap of 0. And it does it for all the temperatures, all the way up to 2,400 Kelvin. You can change what that temperature range is. There's some parameters for that. But basically, given the parameters it gives you, it's going to print out for every temperature a snapshot of the probabilities and the ensemble average properties for that particular temperature. Okay. So with that, I'm gonna wrap up. I'll open it up for some questions, and if not, we'll move on. Okay. And let me know if there's any questions. I'll give you another minute just to post them on the chat, and if not, we're gonna move on. Nope. All right. Well, that wraps up the POCC session. Feel free to email me if you have any questions or post it on Slack. But otherwise, that's it. Thank you for your time.